this lecture we will see the relations between transfer matrices and the twist parameter we have obtained, and also we will analyze one of the basic optical cell known as photo cell. Also we will introduce a new parameter, namely dispersion, which takes care of the dynamics of the particles which have momentum deviated than the design. So we'll start this. Now, solving the Hill's equation, we have seen two methods. One is the piecewise solution, in which we have break down the optics in smaller pieces, and then in each piece, keeping the k constant, we have obtained the solution. This is similar to what we solve a differential equation using the numerical method. Means we broke the equation in different smaller segments, and each segment we solve the equation. And second and more elegant way was to introduce the solution using some optical parameters, twist parameters. And when we were obtaining the solution by this method, we have got the invariant of motion, namely as emittance. In this case, if k is periodic, then we can obtain solution in which twist parameters are also periodic. Means in the case of periodic k, there may be a possible range of solutions among which we obtained those, choose those parameters which are periodic in nature. We say this is the meshed solution. If we know values of twist parameter two locations, can we connect the particles trajectories or particles coordinate between these two parameters, between these two locations? If yes, we can have a relationship between the twist parameters and matrices, because matrix connect the coordinates between these 2 points, and if we can connect these two coordinates at these two locations using the twist parameters, we can have one-to-one relation between the matrices and twist parameters. So we are going to do that. Now, as Hill's equation, we have a general solution in this fashion: x is equal to a root beta cos phi plus b root beta sin phi. Here beta and phi are the function of the s, and because this is a second order differential equation, so we have two constants of integration a and b. These constants are determined using the initial conditions. And if we differentiate this x with respect to s, we get x prime, and which is a alpha root beta cos phi, because we have, when we differentiate this beta root beta, we will get 1 upon 2 root beta d beta by ds, and 1 upon 2 beta prime is minus alpha, which is written here minus alpha upon root beta cos phi. Then we will differentiate this phi, so we will get minus a upon root beta sin phi d phi by ds, and d phi by ds is 1 by beta, so this root beta and 1 by beta will give you the 1 upon root beta, which is 0, 1 by root beta. Similarly, we will differentiate this term, so we will get alpha upon root beta sin phi and b upon root beta cos phi. So this gives you the x prime. And as I have told you earlier that these a and b can be determined using the initial conditions. So let the initial condition like this. Let the initial phase phi is equal to 0, and the amplitude function or twist parameter beta has the value beta 0 at that location. And the initial coordinates of the particle be x0 and x0 prime. So if here we put x is equal to x0 and a, then root beta is root beta 0 because it is the initial, then cos phi because we are taking initial as 0, so cos phi will be 1, and here it is the sin phi, so initial phi means 0, so this term will be 0, so we will have x0 is equal to a root beta, which is written here. Similarly, we will obtain the initial x prime initial is x prime initial 0, because sin phi itself is 0 at phi is equal to 0. So these are the two equations which relates initial coordinates to initial twist parameters. And using these two equations, we can obtain the A and B. So now here, constant values of A and B are as a function of initial parameters. Initial coordinate x0 and initial twist parameters beta 0 and alpha 0. Now we can put the values of this A and B in this solution. So we do that. After a little bit of algebra, means when we will put the value of this A and B in this equation and arranging the terms together of the x0 and x0 prime, you will get x is equal to root beta upon beta 0 cos phi plus alpha 0 sin phi, and coefficient of x prime 0 will be beta root beta sin phi square with the square root. Here beta, you can say, suppose this is the orbit of the synchrotron and this is our initial point where we are defining beta 0, alpha 0 and phi is equal to 0. This is our initial point, And second point is, say, here where we are talking about beta, alpha is the twist parameter, and between these the phase advance is phi. So this beta and this beta are at this location, these are at this location, and this beta 0 and this beta 0 are the parameters at initial point. So now here you can see that x has been written down in terms of x0 and x prime 0, means in terms of the initial coordinate. So now the coordinates of here x and x prime, here the coordinates were x0 and x0 prime. So now x has been written down in terms of x0 and x prime 0. We did this using the transfer matrices. Similarly, x prime can also be written down using these values of A and B, and when we do a little bit of algebra, we got this equation. So now these two relations give us the coordinates at another point here in terms of the coordinate of the initial point. So this is similar to the transfer matrices. So if we compare these terms using the transfer matrices from here to here, means suppose we have M12 transfer matrix from point 1 to 2, which we can obtain using the multiplying transfer matrices of each element which occurs between these 2 points, then that matrix and this matrix should be the same. So now this you can see is exactly in the shape of transfer matrices. But this transfer matrix contains the twist parameters as the elements. Means we have now transfer matrices in terms of twist parameters. We can also obtain the transfer matrices in terms of the magnetic strength K, magnetic effective length L, etc., which we did earlier using the piecewise solution. Then these two matrices must be equal because these both are the solution of the same equations. So if we do that, we equate these elements, we get the connection between transfer matrices and twist parameters. Now here you can see that if suppose this is a orbit of the synchrotron and this is our initial point, as I said, initial point, and this is our final point or point 2. If we move the point 2 and reach here after one turn, in this case beta should be equal to beta naught and alpha should be equal to alpha naught. When you will do this, you will get beta upon beta naught here, beta upon beta, and this will be cancelled out. So you will have cos phi plus alpha sin phi. Here beta beta naught will become beta because beta naught equal to beta, and here 1 plus alpha alpha naught upon beta beta naught. This term will become minus 1 plus alpha square because alpha naught is equal to alpha and beta naught is equal to beta, so root beta beta naught will be beta. So this is gamma, which is written here, and similarly these beta naught and beta will be cancelled out, so we will have cos phi plus alpha psi. So this matrix is for the one term where we have periodic solution of these parameters. Means if we want to know the transfer matrix of one complete term in terms of this parameter where we are choosing the periodic solution, then transfer matrix is this. Now this matrix can be written down in a very interesting form. Our matrix was cos phi plus alpha sin phi, beta sin phi minus gamma sin phi, and cos phi minus alpha sin phi. This was our one term matrix which we obtained earlier. Now this can be written down in this fashion, in the form of summation of two matrices. The first matrix is cos phi 0, 0 cos phi, and second matrix is alpha sin phi, beta sin phi minus gamma sin phi minus alpha sin phi. So you can take common cos phi here and here sin phi. So we will do that. So 1 0 0 1 and alpha beta minus gamma minus alpha sin phi. Now you can see that this is the unit matrix 1 0 and 0. And if we multiply this matrix with itself, then what we will get? We will see this alpha. We will get alpha square minus gamma beta here, and alpha square, you know that alpha square plus 1 is equal to gamma beta. So alpha square minus gamma beta will be minus 1. So this will be minus 1. This element will be 0. This element will be 0. And this element again will be alpha square minus gamma beta, which is equal to minus 1. So you here you get identity matrix, and here this matrix is that kind of matrix whose square gives you the identity matrix with minus sign. Means we can write down this in this fashion. The square of this matrix is minus unit matrix. Means one term matrix can be written down as unit matrix cos phi plus j sin phi. This is similar which we write down as e raised to eta phi is equal to cos phi plus eta sin phi. Means one term matrix can be written down in the Euler form. In the Euler form, what is the use of this? Suppose you want to know m one term power n, means after n terms what will happen. So using this relation you can obtain any power of m one term very easily. And another important property of this matrix is the trace. This matrix again I am writing for your reference: cos phi plus alpha sin phi, here beta sin phi, here minus gamma sin phi, and here cos phi minus alpha sin phi. Now you can see the trace will be cos phi plus alpha sin phi plus cos phi minus alpha sin phi, and this will give you 2 cos phi. Now for bounded motion, phi should be the real quantity, and phi should be the real quantity means 2 cos phi must be lesser than 2 and greater than minus 2, because cos phi should be less than 1 and greater than -1. So 2 cos phi should be greater than -2 and less than +2. So modulus of trace of our matrix must be less than 2 for stable motion. What does that mean? Suppose we are connecting various magnets for making the optics like this, and now by putting matrices of each element, so first element is drift, then a focusing lens, then drift, then a defocusing lens, then drift, then dipole magnet, then drift, then a focusing lens, then drift, then a defocusing lens, then drift, and we multiply these matrices to get an overall transfer matrix. And if we found that the trace is greater than 2, means no bounded oscillatory betatron motion is possible in that kind of optics. So we have to change the strength of our magnets so that trace becomes less than 2. And in case of synchrotron, no motion will be possible, or synchrotron cannot be run if trace is greater than 2 for that matrix. So one-turn matrix in the synchrotron should have trace lesser than 2 for stable motion. So we have to check whether our matrices, overall matrix, produces a trace less than 2 or not. If not, then we have to change our optics accordingly. Now in one complete turn, means we started from the initial point, and in the synchrotron we again reached to this point. This is one complete turn. If the phase advance of this one complete turn is phi, this is the phi. So phi by 2 pi, this will give you the number of betatron oscillations in one complete turn. The betatron oscillations, number of betatron oscillations in one complete turn is known as betatron tune. And this betatron tune is very, very important parameter for analyzing the beam dynamics in synchrotrons. We will see a little bit about of betatron tune when we will study about the chromaticity in later chapters. There will be two betatron tune, one for the horizontal plane and one for the vertical plane. Now we will analyze the tools which we have learned so far. Using those tools we will analyze some optics. So let the very simple optics here. Some focusing quadrupole, then drift space, then defocusing quadrupole, then drift space, then focusing quadrupole, then drift space, then defocusing quadrupole, and then drift space, like that. This is repeated. Means this is a periodic optics in which this basic cell, you can say this basic cell has been repeated many times. Here it is the focusing quadrupole, so F, this is drift space, means open space, you can say O. This is again a defocusing quadrupole, so you can say this is D, and again open space O. So this kind of optics is F, O, D, O, photo optics. So this cell is photo cell. And now you can see that in this figure there is a repetition of 4 such cells, and it may continue like that. Here we are assuming a very simple optics, means focusing quadrupole and defocusing quadrupole have the same strength in magnitude. Sign wise will be different. Focusing quadrupole has -k strength and defocusing quadrupole has the k strength. So strength in magnitude are same for both the quadrupole magnets, and length of each drift space is same. Means this drift space has the same length as of this drift space, and all other drift space also have the same length as of this. So now if we draw one cell only which is repeated, then this will be look like this. So from point A to point B we have one photocell, and here you can see that when we obtain the cell in this fashion, in this cell this quadrupole magnet is half only, and this quadrupole magnet is also half. and this is the full quadrupole magnet in this cell. The remaining half will be in the next cell, and this remaining half will be in the previous cell. So now designate this drift space by L. This is the length of the drift space. Consider these quadrupole magnets as the thin lines. Means we are ignoring the length of these quadrupole and taking it as a point focusing lens. So from start to symmetry point, I am talking about this point, symmetry point. You can see that this is the symmetry point. Means here you have focusing quadrupole, length and defocusing. Then you put a mirror at this location P, you will get the complete optics. So P is the symmetry point. So up to symmetry point, if we calculate it, the remaining will be the same. So M of half defocusing quadrupole, M of drift space length L, and M of half focusing quadrupole. M means matrices. So these will be the transfer matrices, and in this order, if we will multiply, we will get the matrices to the symmetry point. So let us do that. The first half cell will be, first of all, the particle will see the focusing lens. So 1, 0, minus 1 by f1, then a drift space of length L, and then defocusing quadrupole of length L. Up to the half cell, defocusing quadrupole is also half. Remaining half will be after symmetry field. So here what we are writing down F, this is the focal length of the half quadrupole. For full quadrupole, the focal length will be half of this. So after multiplying these three matrices, we get this matrix. And you can see that this element is with minus sign. Means this shows overall focusing in this particular plane. In later half, after the mirror symmetry, the order of the focusing and defocusing magnet reverses, and when we multiply it, we get matrix similar to the above. Here plus sign and here minus sign will be there. Now if we multiply these two matrices together, we get a complete matrix of the photocell. And so complete matrix of the photocell will look like this. These two elements are equal, and this is 2L1 plus L by F, and this again shows the focusing characteristic of this photo. Now if solution is periodic, if we want to see that solution which is periodic in nature, then this matrix must be equivalent to a one-term matrix. Means what we can do, this element will be equivalent to beta sin phi, and this beta will be the beta at the location of the starting point of the cell, where beta in the focusing plane will be the maximum. Why maximum? We will see that. So we have made this kind of lattice. This is our cell. This is focusing quadrupole, this is defocusing quadrupole, this is again a focusing quadrupole. So after focusing quadrupole, before focusing quadrupole, beam will have like this, and this magnet will focus the beam, so size will again reduce. So this will give a location of maximum beta. Means at this location d beta by ds will be 0, means at this location alpha will be 0. Similarly alpha will be 0 here, and after this lens, after defocusing quadrupole, again beam will become divergent, so this will have a beta minimum point. This point is beta minimum point, and here again alpha will be 0. So now if we will compare element by element, so beta sin phi will be 2L1 plus F, and because here alpha is 0, and we know that gamma is equal to 1 plus alpha square by beta, alpha is 0, so gamma will be 1 by beta. So at this location we can write down that this quantity, which is equal to minus gamma sin phi Because alpha is 0 at this location, so this will be minus 1 by beta sine. So this element should be equal to beta sine phi, and this element should be equal to minus 1 by beta sine phi. And we did this. These are the two relations. Now, if we divide this equation by this equation, then sine phi will be cancelled out and only beta max will remain there with square sign. And here you will get 1 plus L by F upon 1 minus L by F. So this gives you the value of maximum beta at this point. This value of maximum beta in terms of magnetic or optics geometry means what is the length of the discrete space, what is the focal length you have chosen for the quadrupole. Using these parameters you can obtain what is the value of beta max here. This beta max is for a particular solution which is periodic in nature. So this beta max will give you the periodic solution of this Frodo cell. So using these two transfer matrices, comparing these two matrices, one obtained by piecewise solution and other one obtained using the twist parameter, we can get this solution or values of these twist parameters at the different locations of the optics. If we multiply instead of dividing these two equations, beta will cancel out and we get the value of the phase sine phi. So sine phi will be this. So now we get beta as well as phase advance in this cell. Similarly, M11 element with one-term matrix. In one-term matrix, we write down cos phi plus alpha sine phi and beta sine phi, then minus gamma sine phi, and then cos phi minus alpha sine phi. Because at that location alpha is 0, so this will only cos phi, and cos phi is written here, it is 1 minus 2l square. And because cos phi must be smaller than 1 and greater than minus 1, when you put these limits, you will get the focal length of half quadrupole should be greater than the drift space length. Means if you want to make a stable photocell, this condition has to meet. Means the chosen quadrupole should have the focal length greater than the length of the drift space between the two quadrupoles. Now as cos phi is 1 minus 2 sine square phi by 2, so sine phi by 2 is L by F. Why we are doing this kind of calculation here from cos phi to sine phi by 2? Because sine phi by 2 will give the phase advance of the half cell, and at the mirror symmetry we have seen that there will be beta minimum. So by knowing these elements we can obtain what is the value of beta minimum in this photocell. We have obtained the values of beta max, now we will obtain the values of beta min. Because up to the half point, starting point will have beta max, and at the symmetry point you will have beta min. So you square root of beta min, beta max, and multiplied with sine phi by 2, because we have either here at this location. Now one term matrix will not be used here. Here we will use complete matrix, that is root beta 2 by beta 1 cos phi plus alpha 1 sine phi and root beta 1 beta 2 sine phi. This matrix will be used here because up to half cell no periodic solution will be there. Periodic solution will be for full cell. So this is written here basically. So using this, now we know what is the value of beta max. Put that value of beta max here, put the sine phi by 2 from here, and you will get beta minimum. So now you have beta max, now you have the values of beta min and the phase advance. Means you have obtained values of twist parameters completely at different locations of this cell.